In this set of video lectures, we are going to look at work, energy, and power. Okay, and we are going to define work from scientific point of view, not in our everyday language. Because in our everyday language, when you think hard also, you say that you are doing some work. But the scientific definition of work is very strict. So how is that defined? Suppose consider a point and you're applying a force on that point. This point may be a point on an object or something, so that doesn't matter. So a force of F Newton is applied on a point, and let me call this point of application of the force, point of application of the force, and the point is moved from here to here. As a result of application of the force F, the point is moved from here to here. That means the point of application is displaced. So the amount of displacement is this much. So let me call it S. Then the amount of work done is equal to the product of force applied and the displacement of the point of application. Displacement of the point of application. So it is point of application of the force. So this is how work is defined from physics point of view. Here we are also going to see another important thing here. Force is a vector and displacement is also a vector, but work done is a scalar. You obtain a scalar by multiplying two vectors. So we call this scalar product of force and displacement is work done. So work done is the scalar product of vectors force and displacement. So how else force is kind of represented in the form of a vector? Usually you write force as F and displacement as S. But because these two are vectors, we usually just put a overhead arrow on these to say that they are vectors. Hence, the work done is the product of force vector multiplied by displacement vector. Here, this is a scalar product, right? Because you need to yield a scalar. So in physics, we refer to that as a dot. So it is the dot product of force and displacement. So scalar product is also called dot product. So dot product of force and displacement is the work done. So we will come back to this dot product because whenever you have a dot product of two vectors, you are supposed to write like this. So this is the definition. We will come back and see why it is written like that. So suppose force vector can be written as F and displacement vector can be written as F. Yes, that means I am only taking the value but not the direction. So whenever I write this force vector's value and displacement vector's value, because it is dot, we often say that it is cos theta. So we are going to do some problems on this in the later part of the videos, or maybe after 3 or 4 videos we will be doing problems to explain why this is so. So work done is the product of F S cos theta, like that. Here force is in this direction, displacement is also in the same direction. In this case theta is 0 degree. If theta is 0 degree, cos theta equal to cos 0 degree, that is 1. If force and displacement are in the same direction, work done is just simply force and displacement. Here work done is positive. Sometimes if a vehicle is there, suppose let me focus on the wheels are going forward. When the brakes are applied, brakes actually try to stop the wheels that act in the opposite direction. So the braking force and even after applying the brakes, the wheels will move some distance and stop. So the displacement of the wheel is in the forward direction, whereas force is acting in the backward direction. So this is the direction of displacement, this is the direction of force. So the angle between force and displacement is 90 degrees. So force and displacement is total of 180 degree. So if you write cos theta, that is cos 180 degree, cos 180 degrees value is -1. If force and displacement are opposite to each other, F S into cos 180 degrees -1, so we will be getting minus Fs. That means work done is negative. If force and displacement are in the same direction, work done is positive, and force and displacement are in the opposite direction, work done is negative. And imagine another example of a negative work done. Suppose you have a syringe here and you close the syringe and there is the piston like thing here. When you try to press the piston, there is some air locked inside. You have closed the syringe. When you push this, the air inside will not allow it to compress. So the air pushes this side. Despite that fact, you are pushing the piston so that the piston is compressing the air inside. All the displacement is taking place this way, but the air inside is opposing it. Here force and displacement are opposite to each other. In such case, work done is negative. Another thing, what if force and displacement are perpendicular to each other? Suppose a person is carrying a luggage on his head and he is walking this way. Let us try to just look at the diagram of this. So this is the luggage, and if this luggage's mass is m, downward gravitational force is mg, and the person is only balancing the weight of gravity on his head, but to move this luggage on this direction he does not have to put in any effort. So when a person is walking forward this way and the displacement of the luggage is in this direction, whereas the gravitational force is perpendicular to that, the angle between the gravitational force or the force and the displacement here is 90 degree. Then the work done is force multiplied by displacement into cos theta. Theta here is 90 degree, so it is cos 90 degree. So the cos 90 degrees value is 0, and hence work done is 0. What is the work done in carrying a load on our head and walking? So that work done is always 0. But for what we are exerting? Actually, we are supporting the weight of the luggage on our head. That is what appears to have been exerting some effort, but actually to move the luggage from one place to another place, you are not expending any force, you are not exerting any force, whereas all the effort that you do, the force that you apply is to balance the gravity. But to move the luggage along this horizontal line, you do not have to do any work. In general, force is the scalar product of work done is a scalar product of force and displacement. Work done is measured in joule because without energy you can't be doing work. So the amount of work done is by spending some energy. So the amount of work done is equivalent to the amount of the energy spent. So work done is actually the amount of energy spent because it is the amount of energy spent. Its unit is joule. In SI system it is joule, in CGS system it is hertz, and the force, the SI unit of force is Newton, which is often represented by the capital letter N, and the displacement is meter. So in CGS system the force is measured in dyne and displacement is measured in centimeter, which implies we can write in SI system joule, 1 joule is equal to 1 Newton meter. So we can also be written as 1 Newton into 1 meter. And in CGS system, erg is equal to dyne into centimeter. Then what is the meaning of that? 1 erg is 1 dyne force acting on an object to move it through 1 centimeter. Then what is 1 joule of work done? 1 joule of work is done or is said to be done if 1 Newton force acts on an object to move it through 1 meter distance. So the units of work is equal to units of energy. In SI system, we call it joule, or it can be represented as Joule. It should not take plural form. In CGS system, we call it ergs. So no plural form. So it is in CGS system. So the representation itself is ERG and no abbreviations or something of that kind. So work done is force into displacement. Unit of work done is unit of force into unit of displacement. If work is represented in SI system, the unit of work done is joule, unit of force is Newton, unit of displacement is meter. So 1 Newton into 1 meter is 1 joule. So what is the meaning of it? So what is the definition of unit of force? What is the definition of unit of force? Unit of work done, sorry. Definition of unit of work done. So the unit of work done is joule. That means definition of unit of work done is definition of joule. What is the definition of joule? Definition of joule means definition of 1 joule. Definition of 1 joule. So the unit of work done is joule, and joule means 1 joule. What is 1 joule? If 1 Newton force acts on an object to move it through 1 meter, then the amount of work done is said to be 1 joule. Okay, because 1 Newton force acts on an object to move it through 1 meter, then it is 1 joule. What about ergs? In CGS system, we know that the unit of work done is unit of force into unit of displacement, and cos theta I didn't write because cos theta is either adjacent side by opposite side. So the cos theta, sin theta, all such trigonometrical quantities are the ratio of two sides, right? Both the sides units will be the same, so they do not have units. So the CGS unit of work done is erg, CGS unit of force is dyne, and CGS unit of displacement is centimeter. And work 1 erg is 1 dyne force acting on an object to move it through 1 centimeter. So the definition of unit of work done in CGS system is if 1 dyne of force acts on an object to move it through 1 centimeter, then the amount of work done is said to be 1 ergs. Okay, then what is the relation between joule and ergs? Relation between the SI and CGS units of work done. We know that in SI system we call it joule, in CGS system we call it ergs. So 1 joule is 1 Newton into 1 meter, which can be written as 1 Newton meter. But in the previous chapter in laws of motion, we have already discussed that force is mass into acceleration. Unit of force is Newton. and unit of mass is kilogram, and unit of acceleration is meter per second square. But in SI system, Newton is kilogram meter per second square. In CJ system, force is measured in dyne and mass is measured in gram. This distance is measured in centimeter and time is measured in second. Same thing. So 1 dyne is gram centimeter per second square. 1 Newton is kilogram meter per second square. Then Newton can be written as, that means 1 Newton can be written as, kilogram can be converted into 1000 grams and meter can be converted into 100 centimeter, and second power minus 2 we don't need to do anything. So this 1000 into 100 is 10 power 5 or lakhs gram centimeter per second square. So gram centimeter per second square is dyne. So on the left hand side it is Newton. So 1 Newton is 10 power 5 dynes. So no plural. Here the same way 1 joule is Newton. So 1 Newton is actually 10 power 5 dyne, 10 power 5 dyne, and 1 meter. So 1 meter is 100 centimeter. So 1 joule is 10 power 5 into 100, 10 power 5. 100 can be written as 10 power 2 dyne centimeter. So dyne centimeter. So 1 joule is 10 power 7 dyne centimeter. So we know that in CJ system 1 erg is 1 dyne into 1 centimeter. So this is nothing but ergs. So 1 joule is 10 power 7 ergs. That means if a work of 10 joule is done, then the amount of that 10 joule in CJ system is 10 times joule, but 1 joule is 10 power 7 ergs. So like this we will be doing another things related to work done. So let us stop today's discussion with this. Then we will proceed further with some more examples to get some more clarity as to how work done is calculated in different situations. We'll do it.